Creating an interactive globe in a web interface might seem like just slapping a texture on top of a 3D sphere, but it's a little more complicated than that. We're going to have to go through quite a few steps in order to get this to work. The first thing we have to do is create a sphere. This is what's going to act as the actual globe within our Three.js piece. Second thing we need to do is map a texture on top of it. What do I mean by that? I mean we need to take a 2D image and map it over a 3D image. I'll show you how to do that. We need to sharpen the rendering because when we do that at first, well, this is going to be a little jagged. We want to make sure that this looks good on mobile devices, retina devices, and wherever we are using a high resolution display. And then we're going to get to the meat of this tutorial. We need to edit this texture and its surrounding atmosphere using custom shaders. A shader is essentially a program that determines how your 3D object looks on the screen, both in regards to vertex positioning and also in regards to pixel color. All the materials that Three.js already uses, such as a mesh basic material, a mesh fong material, these are all custom shaders that Three.js provides for us. But if we want to write something completely custom to create something such as this atmosphere effect with a really nice glow, well, we need to do that ourselves. So I'm going to show you how to write your own custom shaders using GLSL. We're going to add in mouse interaction. As you can see, the globe is spinning as I move my mouse across the screen. Just a little something to make the piece turn out a little nicer and surprise the user for whoever is visiting your website. And then we're going to add in some background stars. If you look really closely, we have some nice little stars in the background, all randomly generated. And then finally, we're going to add some HTML and CSS on top of that. So many tutorials I see out there show you how to create something like this, but not how to integrate it on an actual website. It's so important because you want your websites to look cool, right? Well, you can't just throw a globe on there and people know what your website is about. You need to make sure that you're adding some sort of content along with it. So everything you see within this piece and everything on this list right here is going to be finished within this tutorial completely free of charge. But if you'd like to take this tutorial to the next level, I'm going to be doing an extended edition of this course where we take this globe right here and we add data points on top of it to represent certain things going on in the world. It's essentially the same thing that you see on the github.com website. They have a bunch of different data points with some sort of interaction going on to show where git commits are taking place across the world. We're not going to be doing git commits, but we're going to be uploading some sort of data to our globe to show where exactly those data points are taking place. That'll be available over on chriscourses.com. You can get a link in the description when that is ready. But otherwise, let's get right on into just developing what we have right here. So to start, you'll see that I have a basic Vite project with Three.js imported and the whole scene creation set up. This is an intermediate tutorial, so if you are unaware how to do this, be sure to check out the beginner tutorial that I created. You can check that out with one of the cards right there. Watch about the first 10 minutes or so. I'll show you how to set up Three.js using a program called Vite, which just allows you to automatically reload stuff on your page. It's really nice. And I'll show you everything you need in order to set up a scene so we can begin rendering 3D objects within our browser. So if we go and look at our to-do list, we need to create a sphere. So let's go ahead and start with that. Well, to create a sphere, we need to create some sort of mesh we can add to our scene. So the very first thing we're going to do is create a constant. We're going to call this sphere. This is going to be our sphere mesh. And this is going to be equal to a new 3 mesh. So mesh typically always takes 2 arguments. The first is going to be some sort of Three.js geometry. So within this, we can just go ahead and declare we want to use a new 3. What kind of geometry do we want to use? Well, Three.js provides a comprehensive list of all the geometries available to us. I already know this one off the top of my head. This is going to be a sphere geometry. And this takes 3 arguments. The first argument is going to be the radius of our sphere. How large do we want it to be? Well, we can go ahead and start off with a radius of 5. That's going to make sure that it extends a decent amount within our Three.js world. And then the second argument is going to be how many width segments do we want within our sphere. So if we use a low amount of width segments right here, such as something like 5, it's going to be very polygon-like. When we're looking at Earth from outer space, it's not very polygon-like unless you're in something like Minecraft. And we want to make sure that this is very smooth. So we're going to up this to 50. We want 50 width segments, and then the third argument is height segments, so we're going to add 50 right there as well. And that's all we need to declare our geometry for our 3 mesh. But the second argument that 3 mesh takes is going to be some sort of material. So to start, we're just going to be using the most basic Three.js material there is, and that is going to be a new 3 mesh basic material. And this takes an object as the argument. Within this, we can declare a few options for our material. What option do we want to declare? Well, what color is our material going to be? So we're going to declare a color using hexadecimal format. I'm going to write a 0x, and then we can go ahead and declare the actual hexadecimal numbers we want to create some sort of color on the screen. So if you know your hexadecimal, if we want this to be red, we want to make sure that the first two values are as bright as possible. And the brightest possible rating for the first two values are going to be FF, because the range here goes from 0 to 9 to A to F. We're going to make sure that the red value is as bright as can possibly be. What comes after R? Well, G is going to be our green values, also represented by 2 hexadecimal characters. So we're going to put 00 right here because we want those to be dark. And same thing for blue. We want to make sure that that is as dark as possible. And if we add these all together, well, we're going to get a color of red. So far, so good. We're not seeing anything. And just to make sure we don't have any bugs along the way, it's always safe to open up your console. Just go ahead and right-click on your browser, hit Inspect, go to your console tab, and it looks like we're good to go. No errors showing right now. So looking good, but how do we actually get this onto our scene? Nothing's showing right now. Well, we have our sphere mesh. We can double check this is working just by console logging it out. Console log sphere, and you're going to see that our mesh does indeed show in the console. So we know it's there, we know it's valid, no errors or anything like that. So now what we can do is we can grab our scene object and we can add in our new sphere mesh. So we just want to grab our sphere and add it in there. So it's added in, but why aren't we seeing anything still? Well, this is a basic thing that tricks even me when I come back to Three.js after a while. So right now, when we create our camera with the default Three.js code, where is the camera placed by default? Well, it's right in the center of our coordinate system, right in the center of our 3D universe within the browser. And when we create a sphere, where is that placed within our universe? Well, it's also placed directly in the center. So right now, our camera is actually inside of the sphere. We don't see our sphere because when we use something like Mesh Basic Material, by default, it's only going to color in the outside. So right now, we're looking at the inside of the sphere, but there's no material coloring the inside, so we just see pure black, which blends in with the background. So what we want to do here is make sure that we move our camera back towards us in this 3D space. We're going to go ahead and select our camera, specifically its position, and its Z coordinate. We want to make sure that this is equal to something larger than our sphere geometry radius, which is 5. So you'll see if I do 5 right now, the same radius, we still don't see anything. We're still inside of the sphere. But if we go ahead and change this to 6, well, now we're far enough back to where we can see at least the edges of it. So we're on the right track, but we want to go ahead and take this a little further back, start making this look like an actual Earth. And I would say camera position Z of 10 is in a good spot. So if we go back to do, we created a sphere. And now we want to map a texture onto it. So right now we're just adding a basic color of red on top of our sphere. Well, that doesn't make for a very good Earth. We want to make sure we have some actual image of an Earth wrapped around this whole thing. So if we want some sort of image to wrap our sphere, well, first thing we need is some sort of image. So to find an image, this is very simple. All we have to do is go and search Google. What are we going to search for? Well, we're going to search for Earth UV map. What is UV? Well, we'll be learning as we go throughout this tutorial. Just stick with me for now while we go ahead and get this image wrapped around our sphere. So if you search for Earth UV map, you're going to want to go to images, and pretty much any image you see here you can use within your piece. So feel free to download any of the ones that look like this large rectangle. I really like this one right here, so I'm going to go ahead and grab this. I'm going to right click it, and then I'm going to save image as. Where do I want to save this? Well, wherever I have my project created. I know I created this project within Node. This is going to be 3 globe. And then here is where I can save my image. But it's kind of getting messy in here with all these different file types. So I want to create a new folder called image img, just to be short. And then I want to call this globe. And then I'm just going to hit save. So that's going to download as globe.jpg. I can exit out of this. And now you'll see within my project, I have globe.jpg within my image folder. So that is the first step. Now we need to declare that we want to use this image within our Mesh Basic Material. So what we want to do is go ahead and comment out our color right here. We're no longer going to use that, but rather we're going to be mapping this image to our Mesh Basic Material instead. So how do we go ahead and select our image and specify that this is what our map property here should be equal to? Well, we're going to want to create a new 3 texture loader object. And this has a load property. And what argument does this load property take? Well, the path to the image you want to use. So we're going to go ahead and load the globe texture. Where is that located relative to main.js? Well, all we have to do is go inside of our image folder, and then we're going to grab globe.jpg. It's as simple as that. And once you add that, you'll see the texture is now on top of our globe. It's really that simple to add a texture on top of some sort of geometry. So if we go back to do, we can go ahead and check off map a texture onto sphere. The very next thing we're going to do is sharper rendering. What do I mean by this? Well, if we go ahead and zoom in on our sphere right here, you're going to notice that it's very jaggedy along the edges. That's not very professional looking, not something we really want, especially if we're trying to make this look as realistic as possible. So there are two ways to make this look as clean, as clear, and high res as you can. We're going to go to main.js, and within our WebGL renderer right here, we can add in an options object. And inside of this options object, we can add in a property called anti-alias. And if we set this equal to true, let's go ahead and watch what happens as soon as I hit save. We'll zoom in on one of the jagged edges right here. And if I hit save, you're going to see the jaggedness is taken away. Anti-alias basically just means take away those jagged edges. Make sure that they fade out to create a smooth effect. It's going to be a little more taxing on your computer, but this is such a small project that it really doesn't matter at all. So that is going to be the first way to get rid of the jaggedness and make sure that this is as high res as possible. The second is we are going to select our render, and we're going to set our pixel ratio. What is this going to be equal to? Well, we're going to select our window object, and on top of this we're going to select the device pixel ratio. So let's watch what happens as we go ahead and save this. If you look very closely, you're going to see that the texture actually became more high res. Let me go ahead and exit out of this. And I'm just going to go ahead and toggle back and forth between the two when I turn this on and turn this off. So if I turn it off and turn it back on, you can notice if you're looking very closely that the detailedness of the texture is starting to come in and out. You can especially see this in just like this area right here. Right now it's off, but if I go ahead and turn this on, look at this area start to gain a little bit of resolution as I turn it on. You'll see that's just a little more detailed because we're telling the Three.js renderer to take into account that I'm using a Retina screen right now. And as a result, it's going to give us the most high-res 3D rendering that we can get with Three.js. If you want to make this look even a little more high-res, what we can do is we can zoom the camera out a little bit, because the smaller this is going to be, the more high-res it's going to look essentially. So if I go ahead and make this something like 15, you're going to see that that is starting to look like a real Earth out there in outer space. So if I go back to do, we went ahead and we sharpened our rendering, so that is perfect. So we're in really good shape right now. Honestly, we made a lot of progress with just that little amount of code. But if we go back to the example piece right here, you'll see that this just still looks way better. Why? Because we're using custom shaders instead of just default materials provided to us with Three.js. So next step is going to be making our Earth look like this with this custom shaders to create the atmosphere effect that we see. So how do we create a custom shader essentially? Well, when I'm talking about a shader, I'm talking about a shader program. A shader program is made up of two separate functions. The first one is going to be a vertex shader. All this is a simple function. And second is going to be a fragment shader. This is also a function. Both of these are written in a language called GLSL. So we're going to need to write a function in GLSL for what's called a vertex shader. Let's go ahead and do that, and I'll explain along the way. So we go to main.js. Well, where do we write this function and where do we actually import it? Well, let's just go ahead and start running the function in the correct place. So what I'm going to do is I'm going to create a new folder within my project. I'm going to call this shaders. And within here, I want to create what's known as a vertex shader. So I'm going to call this vertex.glsl. The name of this is totally arbitrary, by the way. It could be whatever you want. I think it just kind of makes sense to call our vertex shader something like vertex, right? So I'm going to go ahead and create that folder and also create that file right here. If you're wondering how I created that, I just have a shortcut within Sublime Text. If you want to create it yourself, you can simply go to File, New File, and then make sure you're creating the new folder directory as you go and create the vertex.glsl file. So this is where our vertex shader is going to go. What is a vertex shader? Well, vertex shader is a function, basically a program that's going to run for every vertex within our geometry. So this sphere geometry has many vertices throughout it. Probably has like one here, one here, one here, one here, one here. All around this has vertices to create this sphere shape. And by using a shader, what we can do is actually alter these vertices in some sort of manner. Whatever our heart desires, we can either move these vertices in different directions based off of some sort of math equation. We can go ahead and change their direction so they're pointing in different ways. We can do all of that with a custom vertex shader. That's why this vertex.glsl file exists in the first place, if we want to edit our vertices in some sort of way. For the most part, we're not really going to be editing the vertices of our sphere, but rather the pixel color within them. So we're not going to be editing the vertex shader too much, but the reason we're using it is because you need a vertex and a fragment shader in order for the main shader program to work. You must have those two together in order for your material to render out on top of your object. So that is why we're using a vertex shader in the first place, even though we're not going to be changing much with our vertices. So enough about the theory. How do we get to writing this thing, and how do we write in a language called GLSL? Well, GLSL is a typed language. You know, with JavaScript, we can just go ahead and create constants. We don't need to declare a type, like what kind of data is a render? Well, it's a WebGL render object. We don't need to declare types like that, and that's, in my opinion, what makes JavaScript great, is because adding on types to things can get really tiresome and cumbersome. At least for me, I know a lot of people like it with TypeScript. But GLSL is a typed language, so we need to make sure that we're declaring the types of our variables and declaring the types of our function. So a vertex shader, it's just one function, and it's going to have a type of void. It's not going to return anything. It doesn't really have a type besides being a function in the first place. And this function is going to be called main, and it's written just like a JavaScript function, just opening, closing parentheses, opening, closing curly brackets. So this main function is going to run once for every vertex within our sphere object. The whole point of it is that it has to set a specific GLSL variable. It always has to set a GL underscore position, uppercase P. You need to make sure that this is uppercase. So for every vertex, we need to make sure that we are setting its position. And this GL position is essentially the XYZ coordinates of the vertex that you're looping over. So if we were to do this with JavaScript, we set it equal to something like an array. The first X position would be something like 1. The Y position would be something like 0, the Z position would be something like 0, and then the fourth coordinate for this is used for translates and transforms. We don't really need to worry about it, just make sure you're always setting it equal to 1. This argument is called W, but these ones are X, Y, Z. These are our main focus right here. If we were to do this with JavaScript, this is what setting the vertex position would look like. What would this do to our actual piece over here if this were valid code? Well, we're basically setting all the vertices to have an X of 1 and everything else to be equal to 0. So if we look at that within our 3D space, we know that this is our center. X of 1 can be somewhere over here. We're not going up or down. So basically just move all of our vertices over here. We wouldn't be able to see our texture or anything like that. So this makes it kind of worthless to do something like this. But just for example purposes, this is what setting this would look like. We need an X, Y, Z, and then the W, which is always going to be equal to 1. But if we were to write this with GLSL, we need to make sure that we are declaring the type. Remember, we always need that type. So what kind of type would something like this be? Well, it would be a type supplied by GLSL of vec4. This is a vector4. If you ever worked with vectors, you can kind of think of them as basically componentized arrays for the most part. Basically, a vec4 of 1, 0, 0, 1 would be equal to the exact same thing as this. They're the same data, just in a different format of representation. But this is valid GLSL, so we're going to make sure that we're setting this equal to a vec4 of 1, 0, 0, 0, 1. So if we save this, nothing's going to happen, because now that we have this shader program in place, we need to make sure that we're applying it to our actual object over here. So if we go back to main.js, we no longer want to use a mesh basic material. We're creating our own shader material, so we're going to call this a 3 shader material. We can no longer use the map with this because we have to do that manually through our own vertex and fragment shaders. So we're going to go ahead and get rid of both of the properties within here. And a shader material takes a couple properties. The most important ones we're going to focus on are going to be vertex shader. That is going to be equal to our filed code over here. And then the second property is going to be equal to a fragment shader. And that's going to be equal to another file in which we're going to create very shortly. So how do we get the code from vertex.glsl over to our vertex shader property over here? Well, we're going to have to import it using JavaScript. Simple enough, right? So similar to what we're doing with importing 3 from our Three.js library over here, we're going to want to import our vertex shader from our shaders directory. And we want to select our vertex.glsl file. So I'm going to comment these out for now, just so we can make sure that we're pulling this in correctly over here. I'm going to refresh, getting a white screen. Something's definitely broken. Let's go ahead and open up the console. If we inspect and open that up, you're going to see that we're getting an error of unexpected token curly bracket inside of vertex.glsl. Well, by default, when we try importing a file type of GLSL using Vite, Vite doesn't understand how to import it. So we need some sort of Vite plugin to make sure Vite understands that all we want to do is take the contents from this file and put it inside of this vertex shader variable. So if we go back to do, we created our first vertex shader. It's not a very good one, but it's there. It's what we need to get going with this. The very next thing we want to do is install that plugin I was mentioning called Vite Plugin String. What is this going to do? Well, it's going to allow us to import a file type like GLSL into this variable right here. So all I'm going to do is open up a new window, and I'm going to search for Vite Plugin String. It's going to be the very first result. So here you can see just by the description, this converts text files to modules so we can import them within our JavaScript. How do we actually install this? All we need to do is run this script right here. So we're going to open up our terminal, make sure we are in the correct directory. I am inside of 3globe. What is my project directory over here? Well, it's also 3globe in the right spot. So now I can run npm install --save-dev Vite plugin string. Hit enter. All this is going to do is make sure this project is installed within our node modules folder, and it's going to make sure it's listed out as a dev dependency, and once it's listed out here, you know you have it installed and you can use it within your Vite project. So let's go ahead and scroll down and see how we actually use this. Well, it looks like we need some sort of Vite config, and all we need to do is declare that this is a plugin within this plugins array. So if we go back to our project over here, you'll notice Vite doesn't come with a Vite config by default. We need to create one. So I'm going to create this the traditional way. Just go to new file, and I'm going to hit Command S right here within Sublime Text. And what I want to save this as, well, I want to save this as this right here. It's going to be Vite config.js. And all I need to do is go ahead and copy this code. We can import Vite plugin string because we installed this separately using this install code up here. All we're doing is declaring it as a plugin within our Vite project. So if we save that, go back to our project, still not working, all you need to do is make sure you are restarting your Vite server. So you can cancel out of your running Vite server by hitting Control-C. That's the default keystroke for exiting out of anything on terminal. If it doesn't work the first time, just hit it a couple times, you'll exit out of it. Once you're exited out of it, you want to run npm run dev to get your server running again. And now you'll see we're back to where we were. All we need to do is add in this Vite config to make sure we can import this vertex shader. So let's go ahead and console log out the contents just so you can see what this looks like. We'll console log out vertex shader. You'll see all it is the exact contents of our actual file. It's just minified a little bit. So that's perfect. Now we can actually declare that we want to use this within that property we created earlier of vertex shader. So if we go ahead and uncomment this, and I go ahead and paste this in and hit save, well, now our new shader material is taking effect, but nothing is showing for a few reasons. One, because our vertex shader is really jank right now. Right now we're setting every vertex position to be in that one location somewhere around here. Not what we want, but also because we don't have a fragment shader in place. There's nothing to actually color in all the space in between these vertices, which is the whole point of a fragment shader. So remember, in order for shader material to work, we need two shaders, a vertex and a fragment shader. Can't say that one enough. Quick JavaScript tip right here before we go on to the fragment shader. If you have a property, such as vertex shader, that is equal to a variable also equal to the same exact name as the property right here, you don't even need to add in the variable, and you don't need the colon. You can just go ahead and add a comment at the end of this. This right here is the exact same thing as what we had earlier. These two are the same. We know that this has the same name as this, therefore we can get rid of it. And the colon, and this is going to work exactly the same. So just a cool little JavaScript tip for you to make sure your code is as clean as possible. So the very next thing we're going to need to create is called a fragment shader. So like I've been mentioning, this works in tandem with the vertex shader. The vertex shader is essentially responsible for placing all the vertices in the correct position to create whatever object you want to create, such as a sphere. The fragment shader's responsibility is filling in the space in between. It's going to loop over every pixel in between those vertices and set its color equal to some value. All this function/program does is it changes a pixel's color. We're going to be looping over all the pixels, and we need to set those pixels equal to some sort of color. That's all we're doing right here. So first thing we need to do is actually create this fragment shader. So inside of the shaders directory, I'm going to go ahead and create a new file called fragment.shaders. fragment.glsl. This is where our fragment shader is going to go. So fragment shader always consists of a base function. We need to declare our type of void. It's going to be main. We need to make sure that this function is always called main. That is the base function. That's just like JavaScript, opening and closing curly bracket. So comparing this to our vertex shader, we don't want to set the position here like we would for each vertice that we're looping over. We're looping over the pixels. So rather than setting some sort of position, we rather want to set a GL frag color and make sure that these are uppercase. Otherwise, this is not going to work. The F and the C. What is a frag color? It's basically the pixel color. So let's go ahead and do this in JavaScript and then transfer it over to GLSL. The JavaScript version of this would be an array. And what are RGBA values if we want this to be equal to something like red? Well, we would want an R of 1, a G of 0, a B of 0, and an alpha of 1. That is going to change the transparency, the very last one. So we know if we were to set GL frag color equal to red, well, for every pixel we're looping over, we're effectively setting that pixel equal to simply red. That's all we're doing here. But we know we're in GLSL, so we need to make sure that this is typed and we're using that language's syntax. So how do we do that? Well, we're going to go ahead and get rid of the bracket and make sure that this is a type of vec4. And at the end, we'll add a closing parentheses. And within GLSL, always make sure you have the semicolon. It is required here. I know you'll always see me write code without semicolons within my JavaScript. Not required there. Makes the code a little clearer in my opinion, but here you absolutely have to use it, so make sure you're doing it. So if we go ahead and set that, now we can actually import this fragment shader within main.js. So same deal as before. At the very top of our file, we can go ahead and import our fragment shader. From where? Well, we're going to go inside of our shaders directory and select what? Well, fragment.glsl. Can console log this out and make sure we're getting it correctly. You'll see it's right there, so that's looking good. Now we can select this and set our property down here equal to what? Well, we're not going to set it equal to anything because of that tip I just taught you. If we were to set this equal to fragment shader right here, well, this is equal to this. It's kind of duplicative. We don't need to do that. JavaScript knows that this is the same thing as using the colon version. But since we just added this as a second property, we need to make sure that these are separated by a colon. So we have multiple properties within our shader material. This is valid JavaScript now. And if we save this, well, we don't have any errors in our console. You shouldn't. If you do, just really make sure that your code within your vertex shader looks exactly like this, same casing and everything, and that your code within your fragment shader looks like this, same casing and everything that we have right here. Should not have any errors right now, but why don't we see anything on the screen still? Well, the issue is we're moving all of our vertices to that one point with an x coordinate of 1. When everything's right there, we're not going to be able to see the actual formation of our object. But if the vertex shader is run for every single vertice within that sphere geometry we have, well, how do we know what to set GL position to when each vertice is going to have a dynamic X, a dynamic Y, and a dynamic Z? Well, here is where we're going to use some boilerplate code from Three.js. The thing is, Three.js by default passes in a few variables into this shader that we can use, including things like the vertice's position in relation to the actual sphere that they are placed on. So when I was first learning this, one of the things that confused me a lot was, where do we actually find these attributes that Three.js passes in? Where is the listing for this? So this is actually going to be in the docs, and this is going to be your best friend. If you need a quick link for this, just go ahead and check the video description on here, and I'll make sure to provide that. But if you ever need to find this on your own, just go ahead and type in WebGL program 3.js, and it should be the very first result right here. So this is the WebGL program documentation. What does this do? Well, it tells you the things that Three.js provides to our shaders by default. Those are going to be, for our vertex shader, something called model matrix, model view matrix, projection matrix. All these different matrices are going to be provided to us by default. And we're also going to be provided the position, normal, and UV for the individual vertex that we are looping through. What are normal and UV? We'll get to that. Don't worry, we're going to be using both of those. But we know what a vertice's position is. This is an X, Y, and Z value. Just for reference, this right here is equal to the vertices what? The X, Y, and Z. So the X would be equal to something like 1. The Y would be equal to something like 0. And then the Z would be equal to something like 0 as well. So this is equal to this. For the vertice that we're looping through, where would that be? It would be somewhere on the right-hand side. We're not going up or down. The X is just going to the right. So Three.js is passing this attribute through to our shader by default. We can make use of this simply by grabbing the name. We can go ahead and delete all this random code I just wrote. We know, if we look at those docs, that that is a type of vec3, but we need a vec4 to supply to GL position. So how do we add in this vector3? Well, we can simply get rid of the first 3 arguments right here for vector4 and just type in position. Position is equal to a vec3. A vec3 is simply equal to 3 arguments. So when we put this right here, a type of vec3, a vec4 automatically knows to just insert this right here. So position right here is equal to the same thing as this because it has the type of vec3. So you might think, well, this is going to put the vertices in their correct position. Each vertice's position is automatically given to us through this sphere geometry. So this should actually draw out our sphere on the screen, right? Well, let's go ahead and save this. We refresh and still not getting anything. Why is that? Although this code logically makes sense, we're assigning the vertice position to the required attribute of GL position, right? It technically makes sense. But the thing is, in order for this to actually display correctly, we need to tell this shader how Three.js is doing calculations behind the scene to translate the 3D objects onto 2D space. So if we open up these docs again, if we scroll on down, you'll see that it leaves a note that you can therefore calculate the position of a vertex in a vertex shader with this code. Where does projection matrix and model view matrix come from? Well, these are the things that are passed through to our shader by default by Three.js. So if we go ahead and grab this whole line of code and replace our current setting of GL position with that instead, and then we go ahead and check out our piece, well, now it looks like our custom shader is working. We're setting everything equal to red, and suddenly all our vertices are in the right spot. So what are projection matrix and model view matrix? Well, these are matrix data types. If you don't know what a matrix is, it's simply an array that is organized in a specific manner. Very similar to the buffer attributes we used within the last tutorial, where every grouping of 3 represented a position of a vertex. A matrix is just simply that. So if I were to write a quick matrix for something like a triangle, I would do -1 for x, 0 for y, 0 for z, and then for the next coordinate, I would go up in the center, so my x would be 0, my y would be 1, my z would also be 0, and then for a final coordinate to complete the triangle, we know that's going to be on the right hand side, so x would be 1, y would be 0, and z would be 0 as well. This is what a matrix is, but typically they're organized in something like squares because it makes it easier to read. So if I were to organize this into a square-like format, like so, we look at this and we know that this first grouping right here is referencing our first vertex. Second is referencing our second vertex. Our third is referencing our third vertex. So all a matrix is it's basically an array that consists of similar groupings of data, such as vertex positions or something else. It can be whatever you want. They're typically organized in square format to make them easier to read, but in the end, a matrix is just simply an array. So when we're talking about projection matrix and model view matrix, these are of the type matrix 4. What is a type of matrix 4? Well, I wrote out this nice little notes.glsl file in which we can see that exactly. So matrix 4 is basically equal to this. It's a matrix with 4 columns, and each column has 4 individual pieces of data to represent some piece of important information. We need these because these determine how our vertices are going to be displayed on the screen within 2D space. Besides that, there's not too much documentation detailing these out, but just know that you need these in order for your custom shader to work and display your vertices in the correct spot on your screen based off of your geometry's coordinates. So one more quick thing I want to go over is how do these multiply together when these are of types of vector 4 and matrix 4. Well, back in notes, you can see how this works when we're multiplying our position, which by default is a type of vector 3, by another vector 3 with these values right here. So this right here is equal to this over here. How do we multiply these two vector 3 types together? Well, it's really simple. If we were to declare we want to multiply these with GLSL, well, we just take the x coordinate of each of these, so it's going to be 1 and 2. So 1 and 2, we multiply these together. What is that going to be equal to? Well, simply, it's going to be equal to 2. Then we do the same thing for the y coordinate, which is going to be this right here. If we multiply 0 by 2, what do we get? Well, it's going to be equal to 0. For our z coordinate, 0 and 1, well, it's going to be equal to 0 as well. So that's how you multiply similar types together, such as if we were to multiply a vec3 by another vec3, a vec4 by another vec4, and so forth. So hopefully that helps a little bit with all this confusing shader stuff we're learning. So concepts aside, main takeaway I want you guys to have for a vertex shader is you need this boilerplate code here in order for your shader to work. If we want to create a cool atmosphere effect, we're going to do that in the fragment shader, not so much the vertex shader. But in order for your geometry to show correctly in the first place, you need this boilerplate code that Three.js provides right here that makes use of these attributes that Three.js is passing into our vertex shader. So now that we have this working, let's go ahead and focus on our fragment shader. So right now, every pixel we're looping through within our geometry right here is going to be red because we're setting it equal to an R value of 1, while everything else is equal to 0. We can easily change this by setting our R to 0, saving. It's going to make it black because 0, 0, 0 is equal to black. If we change the G value here, well, we're going to have a green shader instead. And we can mess around with all these colors by setting random values anywhere from 0 to 1. So in order to get the globe effect working again with a custom shader, what we need to do here is pass through our texture into our shader. Unfortunately, GLSL doesn't support things such as our JavaScript imports like before. Ideally, we would just import our globe image over here from something like globe, but GLSL doesn't support it, so not going to work. It also doesn't support calling some sort of abstracted load function where we can call in a string. Although it'd be easy, unfortunately shaders are hard. So what we need to do is pass our image through using what's known as a uniform. I want you to think of a uniform as basically something we import. You can compare it to this import statement right here. Another good thing to compare it to is going to be props from React and props from Vue. This is something that we pass down into the shader from our JavaScript. So how do we actually pass our texture into our fragment shader? Well, where we have our shader material, we can go ahead and declare a section that is going to be called uniforms. This is going to be equal to an object. And here we can declare all the different variables we actually want to pass through to our shader. So what do we want to pass through here? Well, it's going to be our globe texture. And you might be thinking, well, can't we just load our texture right here and set it equal to this globe texture property? Not the case, because shaders are hard once again. So what we need to do here in order to pass this globe texture uniform through is we need to add an opening and closing curly bracket and add in a property of value. Now we can load our globe texture and it's going to be passed through into our fragment shader. So do you remember how to load a texture with Three.js? Well, it's going to be new, 3, texture, loader. We're going to have a texture loader object, and then we're going to call a load method on top of it, which takes an argument of the location of the file we would like to load. So the location of our file is going to be within our image folder. We're going to call globe.jpg. So given that we have no errors, it looks like we are good to go. And now we can go to our fragment shader, and here we need to declare the uniform that we want to use within it. So if we look back at main.js, our uniform name is globe texture. And above our function right here, we can declare that we want to import a uniform of what type? Well, this is going to be a type of sampler 2D. This is just the default type that GLSL provides for textures. And what is the name of this uniform? Well, it was simply globe texture. And once we do that, as long as we have no bugs, theoretically, our texture should now be available within this globe texture uniform. And now we can use it within our main function. So how do we use a sampler 2D type? Well, this goes within a texture 2D function. And let's go ahead and get this out of the vec4 for now. We'll just put it up here. So we want to go ahead and put our sampler 2D as the first argument within this. Texture 2D comes with GLSL by default. And if you ever need the documentation for this, the documentation out there is not that great because no one is really teaching this stuff. If you need documentation, I recommend taking the function name that we have right here, just typing it into Google, and look for Book of Shaders. This website is probably the best documentation you're going to find on how to use functions like this for GLSL. Everything else is extremely outdated, hard to use, hard to read. The UI is terrible, it looks like it's from the 90s, honestly. So I really recommend using this site for your documentation. If we need to know how to use a texture 2D, we can simply click, and you'll see it gives us the type, and then the arguments we can use within here. So we have our texture 2D that we're using right here, and we know it takes a sampler 2D, which we imported as a uniform, using our shader material, but now it takes a vec2 of a coordinate. Here it says, coord specifies the texture coordinates at which a texture will be sampled. Well, basically the second argument right here is going to take what's known as a UV coordinate. So what is a UV? Well, in our notepad over here, I'll write this down for you. A UV is just simply an X and a Y coordinate. An example is 0, 0. Why are they called UVs? Well, when we're referring to our 3D space over here, well, if we think about our 3D space, the axes that we're using within it, we have an X, we have a Y, and we have a Z. Well, since X, Y, and Z are taken, well, what do we use for a new coordinate system? Whoever created this decided to use U and V. U and V are simply just X, Y coordinates for a 2D texture. The name UV, in my opinion, terrible. It just makes things confusing. Instead of thinking it as UV, I want you to think of this as an X and a Y coordinate, specifically for something that is 2D. That is it. These UV, X, Y coordinates are used to map a 2D texture onto 3D space. So in this little mock-up I put together over here, you can see this is the process of UV, XY wrapping. So we have a texture in the background. This is our Earth. And these orange lines on top of it represent our sphere over here if it were completely unwrapped onto 2D space. So when we want to get an image onto some sort of 3D object, what we're doing is we're unwrapping the 3D object onto a 2D plane, and then we're just overlaying it on top of the image we want displayed. So everything within these orange lines is actually being rendered out on the sphere on the right hand side. So where does the whole UV thing come into play? Well, if we were to unwrap our sphere and it were to look like all these orange lines right here, each of these little points right here is a vertex on a 2D plane. And each of these has its own individual X, Y, UV position. So if I were to go ahead and ask, what are the coordinates for this top left vertex right here? This would simply be a UV of 0, 0. If I'd start moving over to the right, what would the coordinates be for right here? Well, the X moved over a little bit. We're still on a 0 of Y, given that the coordinate system starts 0, 0 at the top left. This right here would be something like 0.05 for U, X, and 0 for Y. So remember, a fragment shader runs for every single pixel being used within our object. And what does Texture 2D do? It returns the pixel color based off of this UV grid-like format. So if I'm looping through all my pixels going from left to right, and my coordinate that I'm passing through right here, vector UV, is equal to that initial coordinate of 0, 0, what is the pixel color for this very first point right here? It's going to be something very dark because this looks like it's black or either blue. But as we keep going through different pixels, well, we're going to be returned different UVs because we have this grid system laid on top of it. Each of these little points right here is going to be a different UV. What is the pixel color on this UV right here? It's probably going to be white. So when we're using Texture 2D, we're simply selecting a texture, overlaying all of our vertices on top of it, and then we're returning the color for each vertex that is overlaid on top of our 2D texture. Hopefully that makes sense. If you feel bad, don't worry. This is confusing for me to learn too. I hope I'm making it a little easier. This is just stuff I tell myself to make myself feel better when I record. So in order for this Texture 2D function to work, we need to make sure we're passing through the associated vector UV for every pixel that we're actually looping through. Where does this vector UV come from? Well, this orange grid just simply represents all the vertices laid out in 2D format. And when we need data related to vertices, where do we go? Well, it's going to be the Vertex Shader. We can actually pass this data through over to our fragment shader. So our fragment shader has access to vertex data, such as our vertices, UV coordinates. So we need to make sure we're setting vector UV within our fragment shader. How do we do that? Well, if we go back to our WebGL program docs and we start scrolling down, you're going to notice by default we're provided a few attributes. This is all the data related to each individual vertex. Might come in useful at some point. And one of those attributes is our UV position. So if our sphere were unwrapped onto 2D space, what would the coordinates of this vertex be with the X and Y coordinate? Well, whatever this is set to is where that coordinate would be. So if we want to pass this attribute right here, which is only available within our vertex shader by the way, if we want to pass this over to our fragment shader, we need to create what is known as a varying. Another confusing term brought to you by GLSL. I love it. So what kind of type do we want to pass through over to our fragment shader? Well, we want to pass through the UV. It's going to be a type of vec2. And we need to give this our own custom name. This is a custom thing that we're passing over. So the name I want this to be is actually going to be vertex UV. Add the semicolon. That's pretty straightforward. A lot of people you'll see call this VUV. I don't really like that because when I was looking at this at first and I'm new to it, I had no idea what that meant. It just confused the hell out of me. It's a little more declarative when you call this vertex UV, a little easier to understand. So this is what we want to pass through over to our fragment shader. But the first thing we need to do is actually set this as our vertex shader runs. So if we go ahead and select our vertex UV varying, what do we want to set this equal to? Well, within this main function, we have access to these specific attributes right here. We just need to set this equal to UV, and that's going to give us the UV coordinate if our sphere was laid out in 2D space for where the specific vertex we're looping over is within that 2D screen. So we set our varying vertex UV equal to the UV attribute, which is provided to us by Three.js by default. Now we can go ahead and make use of it within our fragment shader over here. So if we want to make use of that varying, all we have to do is copy the same line we used to declare the varying in the first place and paste it within our fragment GLSL shader. And now this is going to be equal to something like a vec2 of 0.24 or something like that. If you need to view this in JavaScript terms, you can think of it equal to a simple array like this. This is all we're passing through are just XY coordinates, UV coordinates. So now we have this vec2 vertex UV, we can use it as our second argument within our texture UV function. So if we go ahead and pass that through, what is this going to return? Well, it's going to return RGBA values related to the specific pixel we're looping over based on our texture. So we no longer need this vec4 down here, which is changing our sphere equal to this tealish color. We can go ahead and get rid of that. And we're just going to simply replace it with this texture 2D instead. We paste that in, and voila, just like that, we created our own custom texture shader on our own. We're basically recreating the Three.js library right here, but we're badass enough that we're doing it with vertex and fragment shaders. Sweet stuff. So if we look at to-do, we installed our Vite Plugin String, we created our first fragment shader, we added a texture to our fragment shader using uniforms, and now we have it displaying with our sphere, all custom built. We also transferred over our vertex UV to the fragment shader using a varying, so that is complete as well. And the very last thing we need to do here is add a shade of blue to our earth with some sort of atmospheric effect using a vertex normal. So if we go back to our fragment shader, one of the cool things is we can actually start changing the shade of our texture right here by adding on different vec3s to our texture 2D. So remember, this produces a vec4 by default. If we only want to select a vec3, we can go ahead and add on a .xyz property to the end of this, and that'll allow us to do things such as add on values to our textures x, y, and z. The issue is, while glfrag color requires a vec4, so what we need to do here is wrap this in a vec4 function like so, and since this only produces a vec3, we know we need 4 arguments instead of 3, so we're just going to go ahead and add the 4th one on by adding a comma and indicating that the last one should be 1.0. So here's where the coolness of shaders really starts coming into play. Let's say we want to add a reddish tint onto our globe. What we can do is we can add on to the value of our XYZ right here created from our texture 2D function. So we're going to go ahead and add on a vector 3, which has an R of, let's just say something like 0.5. It has a G of 0 and a B of 0. If we go ahead and add this red value on to our texture's pixel color and save, you're going to see now we have a nice reddish tint on top of this. We can do this for like literally any single color we want. If we want to make this green, we can add on a green tint. We can go ahead and lighten it a little bit to give it a nice effect. If we want to make this a little more blue, we can add on something like 0.1, 0.5, and even go the full distance of 1 to show how we can create fully customized materials here using our own custom shaders. Now, to get the exact look you want, really what it comes down to is playing around with different functions and seeing how those functions affect your texture 2D, whether they're added on, whether they're multiplied on, whether they're divided on, and so forth. It really just comes down to experimentation. So some experimentation code that I grabbed from the creator of Three.js himself consists of an atmospheric effect, which is this code right here. Basically, we're creating an atmospheric intensity. How intense is this atmospheric glow from each individual pixel? And then we're multiplying the value of that intensity by a certain color. This is a mostly bluish color. We're assigning it to atmosphere. And now this is something that we can technically replace vec3 right here with add on to our texture to create that atmospheric effect. Thing is, when we add this code in, well, we're just going to get a complete breakage. Why? Because this code requires what's known as a vector normal. Now we'll go over this code more in depth in a second, but first, what is a normal? Well, a normal is another name for something that represents the direction a vertex is facing. So if we look at this geometry right here, each individual vertex is going to have different pieces of data related to it. What kinds of data are we talking about? Well, its position. What are the XYZ coordinates of each individual vertex? It has a UV. If this were outlaid on a 2D surface, what would the coordinates be, which is X and Y? And then it has a normal. A vertex can technically face anywhere within a 360-degree range. By default, when creating a geometry, each individual vertex is going to have what's known as a normal or a direction associated with it. And a normal is simply just a grouping of data, an X, a Y, and a Z. So if a specific vertex were to be facing in a direction of 1, 0, 0, what would that mean? Well, that means it's facing to the right because it has an X direction of 1, a Y direction of 0, and a Z direction of 0. We're not looking up, we're not looking straight, we're simply looking all the way to the right because we're assigning X equal to 1 right here. When we're talking about normals, all we're talking about are groupings of data that represent which way a specific vertex is facing. So within our fragment shader, given that this atmospheric code requires a vector normal to work, a grouping of data that represents the direction of the vertex we're looping through, how do we get this vertex normal data? Well, same way we got the vertex UV data, we're going to go ahead and declare a varying. Anytime you want to pass vertex data through to the fragment shader, you need to make sure you declare the varying first in the vertex shader, so we're going to go ahead and declare that. This is not the vertex UV, but the vertex normal, the vertex direction. And the vertex normal direction, whatever you want to call it, is going to be equal to, well, some sort of default attribute that Three.js provides to us. I forgot what that is. What is that going to be called? Well, we can go back to our WebGL program docs. That is simply going to be called normal. Simple enough. I like that. Three.js does it right. So we set our vertex normal equal to normal, and now that we set this, we can go ahead and declare we want to use this varying within our fragment shaders. We're simply going to go ahead and paste that line of code in here. And even though we pasted it in here, our code still isn't working. And this is simply because, well, let's look very closely. What is this varying called? Well, I called it vertex normal. What does this code right here have for this variable? Well, this is called vector normal. These are not the same thing. We want to make sure we're passing through the vertex normal, not the vector normal, within this function. And still getting some sort of error, so this is where a little bit of finickiness comes along within the shader world, but thankfully Three.js provides us with some errors. So if we scroll on up, we get an error, assign cannot convert from in high p 3 component vector of float to out high p 2 component vector of float. So what does this mean? Well, basically we have some sort of mismatch. We're passing through a vector 2 to where there should be a vector 3. So a vertex normal, a vertex direction takes an X, Y, and Z, which means it has 3 pieces of data associated with it. So we don't want to use a vec2, we want to use a vec3 instead. And since we're changing this right here, we also need to make sure we're changing it within our vertex shader as well. We'll change that to vec3. And now once you do that, you'll see we have some sort of atmosphere being applied to our sphere. Just to show you that this is indeed working, we can go ahead and get rid of the atmosphere. You see that's it without atmosphere, and then we add it in, we have that nice blue glow surrounding our globe. So here we're using some GLSL defaults, the dot operator, which produces the dot product of 2 vector 3s, and then we're using a power operator which takes our intensity and multiplies it by a power of 1.5. If you're ever curious on how these functions work, like I said, you want to go ahead and take the name and type in dot book of shaders. It has the best documentation for shaders in my opinion, and here you'll see everything you need to know in order to get the dot function working within GLSL. If you want a quick reference for all the functions used in this, well, I created a list of helpful links which will be also available in the description, so you can easily click between things such as GSL documentation within the book of shaders, and also reference that useful Three.js uniforms and attributes page that we've been using so much. So when we're looking at this atmosphere code, don't worry too much about the intensity part. All you really need to worry about is this vec3 right here. This is going to be the shade of color of your atmosphere. So you'll see if I were to go ahead and turn up our red to something like 1, we're going to start getting some pink in there because we still have blue as well. Now we have some yellow, but if I want this to just be pure red atmosphere, we can go ahead and give this a color of 1 for red, 0 for G, 0 for B. The atmosphere I think that looks best is this combination right here, so I'll go ahead and keep that in there. But basically all we're doing is we're assigning all this experimental code over to our atmosphere, and then we're adding on this new shade of color onto our texture. The vertex normal is going to be different for each pixel we're looping through because we're passing it through as a varying, and as a result, that's how we get this nice little effect where the colors are mostly on the edges rather than center, creates for some sort of atmosphere. So looking at to do, we can go ahead and check off add a shade of blue using vertex normal. Now that we have some shader knowledge down, I think we can easily add in the extended atmosphere with a second shader. So let's go ahead and do that, see if we can make this a lot quicker than it just was because we just covered so many concepts. So to add in a second shader, we're not going to add a second shader on top of the same mesh that we have right now. What we're going to do in order to create this bigger glow that we have right here on the edges is we're going to create another sphere object, and we're just going to make it a little bigger than the one that we currently have. So if we want to create another sphere, we can simply copy all of our sphere code. I'm going to comment and say, this is where we create atmosphere, at least the big atmosphere. So here our constant is going to be atmosphere, and we want to add in the atmosphere object. So right now we just have two instances of the same exact thing. This actually isn't going to be using any texture because if we look at our example, well, this isn't really a texture that's being produced for this glow effect. So we can go ahead and get rid of that uniforms object. We're not going to be passing anything through our JavaScript. And this atmosphere should extend past our current sphere geometry coordinates. So if we want to scale this just a little bit, we can call our atmosphere mesh, call its scale property, and then set it equal to 1.1 times the size on X, Y, and Z. Make sure that it's a little bigger. So since this is using the same shader material as our current sphere, well, it's currently overlapping that and it just looks a little bigger. But in order to get that glow effect, we want to create two new shaders. So we're no longer going to use the shader vertex and fragment. I mean, we are going to be using a vertex and fragment shader, but these are going to be different names. We're going to create a new file called atmosphere vertex.glsl, and then a second one called atmosphere fragment GLSL. So for our atmosphere, do we have to alter our vertices for our sphere in any way at all? No, I don't think so. They're just going to maintain that sphere positioning because that is the shape an atmosphere should take, at least with that glow effect. So what we can do is we can simply copy our vertex shader right here and paste it in to our atmosphere fragment shader. We're not going to be using any texture here because we're just going to be generating these colors on our own. No texture required, so we're just going to go ahead and delete our vertex UV. We know we don't need to pass that through. And since we no longer have that varying available, we're going to go ahead and delete this line as well. All this other code is basically boilerplate to make sure that all of our vertices are in the correct position. And just a heads up, make sure you're pasting this within your vertex shader. Right here I just did within a fragment. You need to make sure these go in the right spot. So this should actually be within atmosphere vertex. Good to go there. And then for our fragment shader, we're going to paste in some completed code. Basically, this is all derived on our previous fragment shader code. It's actually something that I experimented with to make sure that I got the best looking atmosphere possible, where it starts off really strong near the center and starts to fade out over time. Basically, we're just taking our blue shade that we used previously and multiplying it by this intensity value based off of our vertex normal, which creates that fade effect for our shader. If you'd like to use this exact code, well, you can get it on chriscourses.com in the description. Just click the button to copy it and you'll be able to use this exact code that you see right here. So to continue, basically now that we have these shaders, we need to make sure that we import them within our file. So we're going to go ahead and copy these two lines right here. We know we don't want to import our vertex shader, but rather our atmosphere vertex shader. And this is being imported from atmosphere vertex. So we're going to go ahead and import from that. And the same deal for our fragment shader. We're going to import atmosphere fragment shader from atmosphere fragment. So those are both imported correctly because our scene is still working. And now we want to set our vertex shader equal to the new shaders that we just imported. So this is going to be equal to atmosphere vertex shader, while our fragment shader is going to be equal to atmosphere fragment shader, like so. So go ahead and add that, and this is the end result of our shader. You'll see if you look very closely, we're producing this glow where it starts off strong in the middle and then fades out near the edges to create some sort of atmosphere. But right now we can't see anything at all simply because our geometry for the shader is larger than our actual globe behind it. So to make our shader actually blend and produce an atmosphere effect, we're going to add on a few effects to our shader material. We're going to paste in a blending property equal to 3 additive blending, which is going to make sure that it blends in with whatever's behind it, and set side equal to 3 backside, which is going to determine where you should be showing shadows. In our case, we're going to show it on the backside just to lighten this up a bit. And you see, once we insert these two right here, well, now we have a good looking atmosphere in place. If we want to go ahead and edit this, make it a little stronger, we can always go back to our atmosphere fragment shader and affect our intensity. So if we want to make this stronger, we're actually going to raise this value right here. You see, the more we raise it, the bigger our atmosphere gets, and we just want to find a happy medium with something that looks realistic, good looking, and not too cheesy. I mean, 0.9, definitely not too hot, but when I was at 0.6, I think that's looking pretty good. That's looking like a very realistic atmosphere effect. Maybe I'll even do 0.65, just tune it to your taste. I think I'm going to stick with 0.6. I think that's the most realistic one I can find. So now, I mean, we've kind of been dealing in 2D. All this looks 2D. We can't even really tell that this is 3D. Let's go ahead and set this in motion. If I go ahead and select our sphere and its rotation, make sure you're doing this within your animate loop. This is what runs over and over again. And I want to go ahead and rotate its Y over time for each frame. I'm going to be adding onto it a rotation of 0.001. Well, now we have a globe that is actually spinning with a realistic atmosphere. It's just there for looks purposes, so we are in great shape. But before we check anything off on our to-do, now that this is rotating, you can see that we do have one bug here, and that is that the backside is way more lit than it should be compared to the front side. So this is a tricky bug to fix on your own, especially if you're new to shaders. And I can tell you right now what's happening is what we're passing through as the vertex normal right here needs to be what's called normalized. More jargon. Basically, same deal as to why our vertices weren't showing initially when we're trying to get this whole thing working in the first place. The position attribute passed through Three.js needs to make sure that it's translated correctly onto a 2D screen from 3D space. We need to do the same thing for our normals. They need to make sure that they're pointing in the right direction within our 2D screen, even though they're being passed from a 3D world. So our normal right here, we actually want to call a GLSL normalize function, which is going to translate these values from a range of 0 to 1, so x will be anywhere from 0 to 1, y will be 0 to 1, and so forth. But we also want to multiply this normal by our normal matrix, which is passed from Three.js. And we want to make sure that we're doing this for both of our vertex shaders. So wherever we're using vertex normal, which is definitely both shaders, we want to copy this line of code. We'll go to our other shader right here. We're going to set vertex normal equal to this normalized version instead. And once we do that, it's going to normalize the direction of all of our vertices to make sure that it's matching up correctly with what's showing there on the screen. So when it finally rotates to the other side, now that we can see the other side, it's using the correct normal value to produce the correct atmospheric effect. And just to make sure my atmosphere is as strong as possible, I want to make sure I edit that within my atmosphere fragment shader. I'm going to change that to 0.6. And this is looking pretty darn good to me. So if I go over to our to-dos, I can now check off add extended atmosphere with second shader. So that's going to be the hardest part of this tutorial. Shaders are notoriously hard to wrap your head around, which is why this is an intermediate course, but I really think we'll breeze through the rest of this now that we have that, especially if you've done the beginner's course in this series. So now looking at our piece over here, you'll see that it has mouse movement associated with it, even though it's already spinning on its axis. How do we add in the mouse movement? Well, we're going to want to add in an event listener for mouse move, and we're going to want to normalize our mouse coordinates. Remember normalizing mouse coordinates from the last episode? We're basically translating our coordinates from our web space to our 3D space. So we need to make sure wherever our mouse is on the screen, we are getting values anywhere from 0 to 1, not something like 0 to inner width or 0 to inner height. So the snippet of code I use for that is this right here. We have an event listener that looks for a mouse move event, and then we're setting a mouse X and a mouse Y equal to the following code. We're just going to make sure X and Y is any value 0 to 1. But if we want to use this code, we need to make sure that we declare a constant called mouse, which is equal to an object with two properties. Looks like mouse has an X property right here. We'll say it's undefined to start. Then we have an undefined Y property as well to start. So now if I console log out this code, which you can also get within the snippet section of the course, by the way, on the course page of chriscourses.com, and I start moving my mouse, you'll see our mouse coordinates range anywhere from, not 0 to 1, but rather -1 to 1, the coordinate system of our Three.js space. So since our sphere is already spinning, how do we add in that secondary spin effect? Wouldn't that alter this spin effect a little bit and kind of throw things off? Well, here's what we're going to do. Beneath where we added in our atmosphere, we are going to create a constant called group, and this is going to be equal to a new 3.group object. And this group object is kind of like a scene. With it, we can call an add method. And what do we want to add into it? Well, whatever object we would like to be within this group, that is simply going to be sphere. Well, now that our sphere is in this group, we have to add our group into our scene. So we'll go ahead and call scene add group. We can get rid of this code up here where we're adding the sphere individually. It's still going to show correctly. And we can still call sphere rotation Y and make sure that that is always rotating. But what we're going to rotate instead with our mouse is going to be this group that we just added our sphere to. So it's basically we're putting our sphere inside of this container. The sphere is always going to be rotating, but now we have the ability to move the group at the same time while that sphere is still rotating. We're not going to be interrupting that rotation. So if we want this to rotate, what we're going to do is select our groups, rotation, Y. This is going to be equal to whatever value our mouse X is, since that's always going to be anywhere from -1 to 1 now. And things should be working, but if they're not, we can just simply go ahead and open up our console. Definitely getting some errors. It just says cannot access mouse before initialization. We're simply going to copy this mouse code just to make sure that it's available before we use it within this animate function. So we just want to make sure we're moving mouse above this animate function right here. Now when we do that, and we go ahead and make this a little bigger, you'll see that even though our sphere is continuously rotating, our group will rotate in whatever direction we move our mouse in. And now this is a lot of movement, a little too much for me. So we can always decrease the value in which we are rotating Y by multiplying it by something like 0.5. And that movement's looking a lot better. But if you look within the example piece, how did I get it so the movement is slow and delayed and it doesn't follow you instantly? Well, I did this using an animation library called GSAP, the same one we used in the last episode on Three.js. GSAP is just a way to interpolate your movement. So if I were to move this with GSAP, well, it would move over time rather than just following me instantaneously. So let's go ahead and get this moving with GSAP. To get this moving with GSAP, we're going to want to open up our terminal. We'll cancel out of Vite right now, and we want to install GSAP. We're going to do so with npm install. Then we're going to call GSAP --save, so it saves as a dev dependency. That's going to run. I look in package.json to make sure it's there. GSAP is there. Now I can use it within main.js. So if I go to the top of my file, I can now also import the module GSAP from GSAP. So now back where we were setting our group rotation, we want to call GSAP.to. What object do we want to animate? Well, we want to animate our group rotation object. Now within this group rotation object, what properties does it have? Well, it has an X, a Y, and a Z. We want to animate the Y. And that is going to be equal to our mouse X times 0.5. So we can delete this initial set code right here, and we're going to use the GSAP version of it instead. And if you refresh and things aren't running, just make sure you restart your server. You're going to want to call npm run dev, start it up again. Now things load, and now you'll see it's not instantaneous when it follows my mouse. It's close to it, but there is a little bit of delay, a little bit of interpolation to make this a lot smoother. If you'd like this to be as smooth as possible, you can increase the duration in which this interpolation happens. So if I want to increase interpolation to something like 2 seconds, you'll see it follows my mouse a lot more slowly. That looks a lot more natural than it did before. So looking really good. Let's go ahead and also animate not just our Y, but also our X rotation. So make sure this turns forward or backwards. We're going to have to reverse our Y coordinate system because the Y coordinate system of Three.js is completely reversed from that of a web browser. So we need to make sure we're using negative mouse Y instead. And then same deal, I'm just going to multiply this by 0.5 and make sure you add a comma to the end of that. And that is looking pretty darn good. I might even decrease the rotation a little bit on the X rotation, make it a little lower, something like 0.3. And that looks a lot smoother, a lot better to my liking. Now for a final touch-up, if you want to make sure that this thing is always rotating a little faster than it is right now, you can simply up the rate at which we are increasing rotation Y, like so. And if that's too much, you can even do something like 0.3. Just tune this to whatever your taste is. All right, so that's going to take care of mouse movement. If we go to do, we can check off adding mouse movement interaction. Perfect. So the next thing we need to do is add background stars. How do we do that? Well, thankfully the lessons taught in the last Three.js episode are going to help a lot for this. To start, we're going to need to create a star geometry. This is going to be equal to a new 3.buffer geometry object. That's all we need to start. This is just going to be a completely blank geometry. And then we're going to create a new star material. This is going to be equal to a new 3-point material. It's basically the same thing as mesh basic material. It takes an object. The color we want this to be, the color we want each of our stars to be, is going to be hexadecimal of 3 Fs to declare that it's white. Now in standard fashion, we want to create, what do you think, a mesh? Well, not quite. We're going to create a constant called stars. And this is going to be equal to a new 3, not a mesh, but a points object instead. And this takes the same thing as a mesh would. The points object just works a little differently to make sure that we're rendering some sort of material at each individual point rather than filling everything in. So the first thing we want to add here is a star geometry, so very similar to a mesh, and we also want to add in a star material, also similar to a mesh. And now that we have our stars object, let's go ahead and console log it just to make sure it's there. You'll see that is equal to points, which is perfect. We want to go ahead and add this to our scene, so we'll call scene add stars. So it's added, but why isn't anything showing? Well, in order for this points object to actually work and show stars on the screen, we need to make sure that we're populating our star geometry position attribute. So buffer geometry should have attributes related to positions, normals, and UVs, but really to create points on a screen, all you really need is that position attribute. We don't care about the direction. We don't care about how it's laid onto a 2D space. So all we're going to do is take this bare buffer geometry and make sure we're adding on a whole array of points onto its position attribute. So what I'm going to do is I'm going to create a constant star vertices. This is going to hold all the star positions which we want to place stars across the screen. So we're going to create a for loop that says loop through this about 10,000 times. That'll produce 10,000 stars on our screen when we're ready. And when we're producing stars, we need to create an X, a Y, and a Z coordinate for all of their positions. So what should X be equal to within our 3D space? Well, we know the X position of our stars should be anywhere from the left side of our screen to the right, which means when we're looping through this and generating random values, that the value needs to be randomly negative or positive. So to get a random negative or positive result from math.random, we can simply subtract 0.5. So math.random produces any value 0 to 1. Say we get the low end of that, which is going to be 0. If we subtract 0.5, well, we get a value of negative 0.5. But if we get the high end of math.random, which is going to be 1, we subtract 0.5, well, we have 0.5 as a result. A great way to get a random number anywhere from negative 0.5 to 0.5 and make sure your values are either negative or positive. So we want to wrap this in parentheses, and we want to make sure that these stars are spread out across our x-axis. So we're going to go ahead and multiply this by 2,000, which basically just means our x value can be anywhere from negative 1,000 to 1,000. We're going to do the exact same thing for y, so make sure that they go all the way up and down our screen in random positions. But for our z, we want to make sure that all these stars are actually behind our Earth so the user can focus on the planet rather than having all these stars overlapping in front of it. So rather than use this code that gives us some sort of negative or positive value, I'm going to get rid of that. And instead I'm just going to set this equal to negative because negative values go into your 3D scene. Positive values on the z-axis are closer to you. So now that we're generating an x, a y, and a z, what we can do is select our star vertices array and push in our x, our y, and our z. We're basically creating a matrix. Every 3 data values of this group represent 1 vertice position. So if we console log this out at the end of our for loop, star vertices, you'll see we have an array full of 30,000 randomized star positions, which means we have 10,000 stars which are going to be placed randomly across the x, y, and z axes. So like I said, to get this points object to work, star geometry needs to have a positions attribute full of all the points we want on the screen. So to set this attribute, what we can do is select our star geometry, call set attribute. What attribute do we want to set for our geometry? Simply our position attribute. And our second argument is going to set this position array equal to what? Well, all the star vertices we just produced. But this needs to be equal to what? Well, it needs to be equal to a float32 buffer attribute. And Three.js provides a shorthand object for us to create this very easily. So for our second argument, we can call a new float32 buffer attribute, which is going to take our star vertices array as the first argument, and then it's going to ask how many pieces of data make one grouping. Well, every 3 pieces of data, because in X, Y, and Z, well, that is going to be 3 pieces of data. Basically, all this is going to do is take our star vertices, convert them into a float32 buffer attribute array, which is exactly what we need to set a star geometry position attribute. And when you're creating this float32 buffer attribute, just make sure that you're prepending 3 on there if you're using the 3 dot version. And just by doing that, you'll see now there are a bunch of stars in our background. And you can toy around with these values simply by editing the values within your star vertices loop. If you want to bring them closer to you, you can decrease the Z value right here. And you can always decrease and increase the X and Y values as you need to your wish. But that is going to be, if we look at to do, how you add background stars to your scene. Now finally, we're going to turn this into an actual web page with HTML text. I refuse to let you guys get away without showing you how to put this on an actual page, because I think that is the most important part to any Three.js piece. So we're going to be jumping between this example piece right here and our work in progress piece right here. So in order to get this looking like this is how we're going to mark up our HTML. We're going to go directly in here, and I'm just going to create one base div. And I need to start thinking to myself, well, how do I get our earth over to the right side of our screen? Well, if I inspect this right now, you'll see the earth is rendered on top of a canvas. What if I could put this canvas within an element that had a width of 50% and I just pushed it to the right? I think that sounds like a pretty good idea, because then I don't need to mess with the coordinates and 3D space. It's going to make my life a lot easier. So let's go ahead and go with that. What we're going to do is we're going to put this canvas in its own container with a width of 50% rather than filling up the whole screen. So first, if we look within index.html, we don't actually have our canvas here. Where's the canvas coming from? Well, within main.js, with the default Three.js code, we are appending on our renderer DOM element. And that is just making sure that the canvas is going to the very last element within our body tags. We no longer want to do that. We want to make sure that we can alter where our canvas is on the screen. So back within index.html, I'm actually going to, within this div tag, create a canvas element. And this is where our Three.js piece is going to be rendered, rather than on this one that is being generated for us. So we want to get rid of this document body append child. We're just going to get rid of that completely. But where we have WebGL render, we can add in a canvas property. And all this is equal to is the DOM element we want to put our Three.js piece on, which needs to be a canvas. So we can select that with document.query selector. And we want to select what? Our canvas element. So if we do that and refresh and inspect, you'll see our canvas is sized correctly, but now it is placed inside of our div tags, so we can start altering things such as its width with CSS. So we are off to a great start. Let's go back into index.html. Now let's start marking this up. We're going to have one parent div which acts as a flex element. This flex element is going to force 2 divs to be side by side each other. We're going to have one big div right here and one big div for our canvas on the right hand side. Those are going to be equal to widths of 50%. So this parent div is going to have a class of flex. And then we're going to create 2 divs inside of this. One for our canvas on the right hand side, and then a second for all of our text. This is going to be all of our content on the left. So we refresh, we see our content, and our canvas is beneath it. Even though we have this class of flex, flex is supposed to put these next to each other. Why aren't they next to each other? Simply because we don't have a flex class. Now we can either go ahead and create this class manually with .flex, set its display equal to flex right here, or we can start using some sort of utility CSS framework. I pretty much always use something like Tailwind. I don't like writing CSS any other way. It's just long and tiresome otherwise, in my opinion. So what we're going to do here real quick is import Tailwind CSS and use all those nice Tailwind classes for rapid CSS development. So all I'm going to do is search for Tailwind CSS CDN. Going to be the very first result at installation. I can do a Command F for CDN, and it's going to go ahead and give me this link, which I can take. I'm going to copy that and paste it right above my style tag. I'm going to pull in all of Tailwind CSS's styles. If I save that, you'll see now Flex is taken into account because this is indeed a Tailwind style. And now we can continue using this as needed. So another Tailwind class that we want to use is going to be width 1/2. This is width 50%. We're going to want to put that on our text div. We're also going to want to put this on our canvas div, so width 1/2. And that splits up everything on our screen, but you'll see if I start scrolling to the right, well, we have the ability to scroll, and this should only be taking up the height and width of this actual container we have right here on the right hand side. So in order to fix this, we need to remember within main.js, we are setting our canvas renderer to be the full width and height of our screen. Where are we setting that? Well, we're setting that right here with renderer set size. We're setting it equal to inner width and inner height. Well, we want to set to the container width and container height instead. How do we get that? Well, we need to create some sort of container for our canvas. Well, we already have one, but let's go ahead and create an ID for this. This is going to be canvas container, just so we can select this easily within our JavaScript. Once we have an ID of canvas container, we can go on over to our JavaScript, pull this in as a constant, canvas container. This is equal to document.querySelector. We want to select an element with an ID, so $. What is this called? Canvas container. We can console log this to make sure it's coming out correctly, and make sure you spell this correctly, unlike me. Console logging out canvas container, and there it is. We're selecting the correct element. Now if we want this element's width and height, we can select this element. We're going to replace inner width with our canvas containers offset width. And then we're going to do the same thing for inner height. We're going to select our canvas container and select its offset height. Now with this, you'll see our height is a little messed up. If I inspect this, you'll see our canvas width is equal to 1280, even though our container width is equal to 640. So why is this the case, even though we just told our canvas to be the exact width of its container, which should be 640? Well, the issue is with pulling in Tailwind through a CDN. With Vite's reloading, it's actually running our JavaScript code here first before it actually pulls in Tailwind and those Tailwind classes take effect. How do we fix this? Well, we just need to install Tailwind locally rather than pulling it in through a CDN. How do we do that? Well, back where we just copied the Tailwind CDN, in the sidebar right here, there's going to be an option for using Tailwind without post CSS. We're currently on the option of using Tailwind with this CDN. We don't want that. We'll go ahead and go with the version without post CSS. So we go ahead and click that, and we can just go ahead and simply run this command to get Tailwind within our project. So if we open up our terminal, we make sure we're in the correct project directory, which we are, 3globe, and we run this command. It's going to generate a Tailwind CSS file with all the styles we need to get working with Tailwind CSS. And we can go ahead and prove this by looking within our project and seeing that now we have a file called Tailwind CSS, and it has every single Tailwind style that we need in order to work with it. So now that this is generated and on our local server, we no longer need to pull this in through a CDN. We can go ahead and get rid of all the content within this href and reference tailwind.css instead. So if we do that, go back to Vite, you'll see that this is now sized correctly, and I can no longer go to the right hand side of the screen because all our styles are loaded on time. Quick issue though is that obviously this isn't taking up the full height of the screen. Nothing really is. If the content on your screen isn't the full height or larger, well, you need to declare that specifically. So to make sure that our canvas is taking up the full height, even though no other content is expanding past where it is currently, on our root div of flex, we're going to add on a Tailwind class of height screen, which sets the height of that element equal to what? Well, 100 view height. So if I go ahead and refresh this, you might need to do a hard refresh with Command-Shift-R on Chrome. You'll see that now it expands the full height of the screen. One more thing is looking off though, and that is the aspect ratio of this, making this look like an egg Earth. It's not how Earth looks like from what I remember. So back within main.js, you'll see that we set the size of our render with canvas container offset width and canvas container offset height. Let's go ahead and select that. And remember that our perspective camera up here is currently displaying everything based off the inner width and inner height of our screen, which is the full width and height of the browser window. So we want to make sure we get rid of that and say that our camera aspect ratio should be our container offset width rather than the width and height of the browser. But if we want to use this canvas container constant, we need to make sure that we declare it before we use it So right after our import statement, I'll simply paste in canvas container, and now you see this is sized in the correct place within our browser. Alright, so easy running from here, HTML, CSS wizardry time. So basically what I'm going to do is I'm going to take this example piece, and I'm just going to put it off to the side, and I'm going to try to mimic what I have over here to match up with this. This is exactly how I develop for real clients, by the way, is I have the design open in one window or another monitor, and I try to match up my site to be as close as possible to the design. So for the most part, we can stick within index.html. We just need to make sure that this text looks like this and is in the correct position with Tailwind. So let's go ahead and start by centering our text. What I'm going to do is within this container class for our content, I'm going to add a class of flex and flex call. I don't want to use just a class of flex here because that puts elements inside of this next to each other. I want them stacked on top of each other, which is why I'm adding in the class of flex call. But I still want to be able to use flex movement properties. So now that I have flex on here, I can call justify center, which is simply going to center all of the content within this container to the center of the parent div. Next, we know we need a little bit of padding on the side. I can go ahead and add on some padding to the left and right of this with px, something like 8. That looks pretty close to me. Let's go ahead and change the obvious. Let's go ahead and make the background for this section black with BG black. And now that this is black, we need to make sure our text is white. So on the H1, I'll add a class of text white. My text is now white. That is perfect. And we can start adding in the actual text we're going to use. So this is just some dummy text I came up with. I'm going to replace my new dummy text of gibberish with just that. And then I want a paragraph tag, because this is paragraph text, to contain this text that I stole from GitHub. So that's in there now, but I want to make sure that it's white, so I'll add a class of text white. Looking good, and now I have a button beneath this. This is probably a link. Whenever you have a link, you want to use an anchor tag. So I'm going to add in an anchor tag here. This has the text learn more. And then the class for this, we want to create a big button. So our text is going to be white. Our background is going to be green. Looks like that is a green of 600. Just some sort of shade like that. Doesn't really matter if it's 600, 900, whatever you like, honestly. So right now this is taking up the full width of the container, probably because this is a flex child. We want the anchor tag to be separate from our flex positioning and all of that, so I'm going to wrap it in a div. And that's going to take care of that, but I also want to make sure that this is an inline block, because this should be affected by margin, and we want to make sure our padding takes effect when we add it in here. So if we add in some px of 4 to give it padding on the left and right hand sides, you'll see that's an ample amount, probably not enough though. We'll go ahead and give it a px8, add on a little more. And if we want padding on top and bottom, this is typically less than the padding on left and right hand sides if you want this to look good at least. So we'll add in py4, looking pretty close. I think I'll stick with that. And we want this completely rounded, so we'll add a tailwind class of rounded full, which sets the border radius equal to something like 50 to 100%. So the button looks pretty good. Let's go ahead and get the paragraph text in shape. So the paragraph text is actually some sort of gray. So instead of white, we'll go ahead and change this to text gray of a shade 400, one of Tailwind's many shades. That looks to be on point with the color. And then obviously our headline text needs to be much bigger. So we'll go ahead and add a Tailwind class of text 4XL to enlarge it. Looking pretty close. We need a little bit of space beneath it. We'll add some margin bottom of something like 8. We also need a little bit of space beneath our paragraph text, so we can add margin bottom 8 to that as well. So already looking pretty darn close. What is the difference here? Well, it's going to be the font. Where are we getting these fonts from? They look cool, they look high tech compared to the default that we have over here. Well, these are coming from Google Fonts. So let's go ahead and import those. To import some Google Fonts, we're simply going to type in Google Fonts. Makes sense, right? We're going to click the first result. And what fonts do we want to use? You can use anything you want, but I already came up with a few good fonts for this. The ones I'm using are going to be XO2. And this one's going to be a semi-bold italic. So if I go ahead and scroll down to semi-bold, italic, I can select this style. And it gives me some link code, which I can just simply copy and paste it beneath our Tailwind CSS style tag. So it gives you some instructions on how to use this if you scroll down. Basically, we just need to make sure we create a CSS class with this font family style. So if I copy that, go to our style tags, and create a class of font XO, set it equal to that style that Google Fonts provided, Now if I set my h1 equal to font-exo, you'll see that it just took effect. It looks like this is a little bolder than what we have over here. So if we want to make this bolder without having to go through the whole Google Fonts thing again, we can just go to our URL. And we know that our weight is right here. 600 is typically semi-bold. If we want to bump this up, we can go to 700, which is typically bold. You'll see, yeah, that's already looking a lot better. Now, what about this down here? This looks to be a different font as well. Well, this is a really good paragraph font that I like using when I want something to look very clean and professional. This font is a very standard Google font. It's called Lato. It can be used for almost anything. I like using the regular 400 version. That's pretty much all I need. And when you select the style, it's going to add it in automatically to your link. So you'll see right here we have XO2 and we also have Lato. So if I go ahead and copy just the second link and replace our old link with that, making sure that I change our XO weight to 700 because we did that earlier. Now we can create a Lato class. So I'm going to copy this one style. And beneath font exo, I'm going to create Lato and set it equal to that font family. So now I can set our paragraph text equal to font Lato. And up here, just make sure you're actually calling this font Lato, or else it's not going to take effect. And now, if you look at these two, those are pretty darn close. Let's go ahead and see what these look like full screen. So this is the finished piece at localhost 3001. And this is the non-finished piece. So on bigger screens, what's happening here is this has a max width associated with it. Typically, you want to have some sort of max width associated with your text, so the user's eyes don't have to travel as far from the left and right hand side to read your text. So if we look at this, we know this over here needs to take up half the screen because our canvas is taking up the other half. So we don't want to add some sort of max width to this div right here, which has that width 1/2. We're going to want to add a max width to a div inside of it. We're just going to make sure that all of the child elements are contained within that div. So within this div that we just wrapped everything in, I can simply add an inline style of max width 500 pixels. Don't let anyone tell you that inline styles are bad. I use them all the time. They make sense to me. They get the job done quickly compared to writing a whole new style. Screw that. So now this is looking pretty good text-wise if we go back and forth. The only other difference is this is a little better centered. It has a little bit better visual flow compared to what we have over here. And that is because this div with a max width of 500 is actually centered. And we can center this with MX Auto. We do that, we switch back and forth. Almost exactly the same. Looks like the only difference is the line height. This is really kind of just a taste thing. If we want this to be exact, we can go ahead and decrease the line height with a class of letting, I think tight probably. Maybe letting none. And that's just going to set the line height on this equal to 0. Your line height is going to vary on a font by font basis, so you need to change that accordingly. And now if we switch back and forth, looks like this text is pretty much exactly the same. Only thing different now is the Learn More button is a different font. It looks like the finished piece is Lato. So we go down to our button, add on font Lato. We switch between them. Now these are exactly the same just by using tail and CSS. So finally, the only difference is our shader over here for our atmosphere is definitely brighter on the example piece rather than the one we have. And this is all going to come down to taste. Personally, I like the atmosphere we have over here. It's not too bright. It's not as crazy as this. But some of you might like this one instead. If you want to brighten this up, like I said, you got to go back to your atmosphere fragment shader. And this value right here, you can play around with until you get a brightness level that you like. If you go ahead and increase this value, you're going to get something that's super bright, and that looks more similar to the example piece, although it's not going to fade out as well, so you kind of just have to find a happy medium. That's something that fades out well, and something that's still as bright as you want it. So I'll probably go ahead and set this equal to 0.75, and I think I'm probably going to call it at that, just to match it up pretty close to what we had in the example. If I switch between those two, it just looks like our earth is a little bigger at this point, honestly. I think that glow looks really good, really close to what we have over here. It's just enlarging the earth, which you can do by either zooming your camera in on your piece or just enlarging your spheres all together. So that's going to be it for this one, folks. I know that's a long one, a lot of confusing material in there, but I hope I helped simplify it at least a little bit. If you'd like the follow-up tutorial for this on how to add data points to your sphere similar to what GitHub does on their website, be sure to check out chriscourses.com in the upcoming weeks. Otherwise, I'll see you guys in the next one. Peace.